Hello, welcome. In this short video, let us look at the derivation of conditional mean of one of the components of a vector where it has two jointly Gaussian variables. That is, given the vector z that has two variables x and y that are jointly Gaussian, that is, x comma y follows a Gaussian distribution with the mean vector e of x and e of y and the covariance matrix C, where C is equal to variance of x, covariance of x comma y, and covariance of x comma y, and variance of y. That means, in other words, the vector z follows a Gaussian distribution with the mean equal to this, the mean vector equal to e of x and e of y, and the covariance equal to the covariance matrix equal to C. So, given this information, we want to derive the conditional expectation of x given y. And since both the components of the vector, that is x and y, are jointly Gaussian, we can actually derive this posterior or conditional mean of x given y by looking at the probability distribution of x given y, that is the conditional probability of x given y, which is clearly equal to probability of x comma y over probability of y, that is the joint distribution of x and y upon the marginal distribution of y. Therefore, probability of x comma y, that is the joint distribution, is equal to the posterior or the conditional distribution of x given y multiplied by p of y. So the joint distribution is given by the joint Gaussian distribution function, which is equal to 1 by 2 pi multiplied by determinant of c power 1 by 2 multiplied by exponential of minus x minus expectation of x, y minus expectation of y, transpose into C inverse, which is variance of x into covariance of x comma y. Next is covariance of x comma y, and then covariance of x comma y and variance of y. Whole inverse multiplied by x minus e of x, y minus e of y. So this is a joint Gaussian distribution. We can actually derive the conditional mean by looking at the exponent of this distribution, which can be written as follows. The exponent is equal to x minus e of x, that is expectation of x, and y minus expectation of y, multiplied by the inverse of this 2 by 2 matrix, which is clearly equal to 1 by the determinant, which is variance of x to variance of y minus covariance of x comma y whole squared, multiplied by the adjoint matrix, which is variance of y minus covariance of x comma y minus covariance of x comma y and variance of x, multiplied by the matrix, multiplied by the vector x minus e of x, y minus expectation of y. And this simplifies to x minus expectation of x multiplied by variance of y minus covariance of x comma y multiplied by y minus expectation of y. And the second term is x minus expectation of x multiplied by minus covariance of x comma y, and the other term is y minus expectation of y multiplied by variance of x. And then we have this vector, which is x minus expectation of x, y minus expectation of y. And of course, we have this denominator, which is equal to 1 by variance of x into variance of y, multiplied minus covariance of x comma y squared. So this is the inverse of the determinant of the covariance. Upon further simplification, we have x minus expectation of x whole square multiplied by variance of y. That is the product of this term and this term. And then we have covariance of x comma y multiplied by y minus expectation of y multiplied by x minus expectation of x. And then we have the product of this term and this term with the second, which is again minus x minus expectation of x into y minus expectation of y to covariance of x comma y. The last term is plus y minus expectation of y whole square into variance of x, and this is multiplied by 1 by this term, which is variance of x variance of y minus covariance squared of x, that is square of the covariance of x. Now we have to basically compare this exponent with the exponent of the conditional distribution, which is clearly equal to x minus expectation of x given y whole square divided by the variance of x given y. So by comparing the x terms in this exponent with the x terms in the exponent of the conditional distribution, we have, it is comparing these two, 1 by variance of x given y, that is this denominator should be equal to, that is basically the quotient of the quadratic term, that is x square by variance of x given y. So we have 1 by variance of x given y is equal to the coefficient of the quadratic term, which is variance of y divided by the denominator right here. It is the product of variance of x and variance of y minus the square of the covariance. So which is variance of x, so variance of y minus covariance of x comma y whole square. So this is the inverse of the conditional variance of x given y. And then by comparing the coefficients of the first order term, that is minus expectation of x given y over variance of x given y is equal to, then we have one term here which is minus expectation of x multiplied by variance of y, and we also have the denominator which we can write later. So and the second term is the coefficient of this term, which is y minus expectation of y multiplied by the covariance of x comma y. And note that there is a 2 over here which cancels with the 2ab term here, with the 2 in the 2ab term over from here, and also this term actually repeats. So we also have another covariance of x comma y multiplied by the difference between y and expectation of y, and the denominator should be equal to variance of x into variance of y minus covariance of x comma y squared. Therefore the conditional mean expectation of x given y should be equal to variance of x given y multiplied by expectation of x into variance of y minus covariance of x comma y multiplied by y minus expectation of y divided by this, which is variance of x variance of y minus covariance of x comma y squared. And since variance of x given y is given by the denominator, the difference between the product of variance of x and y minus the square of covariance over variance of y, that is by using this result, we have 1 by variance of y multiplied by expectation of x, that is the prior mean, multiplied by the variance of y minus covariance of x comma y. This should be a plus here. So covariance of x comma y multiplied by y minus expectation of y. This should be plus here too. This implies expectation of x given y is equal to the prior mean expectation of x plus covariance of x comma y over variance of y multiplied by y minus expectation of y. So this is the conditional expectation of x given the other component y or the observations. Thanks for watching.